is well known to all of you. It's our own Tony Barnosky, who's a faculty member in IB and a curator in the UCMP. And Tony's obviously very well known for the work that he's been doing on global climate change issues. And today he's going to speak about that work. He's going to talk about a conceptual framework for forecasting biological impacts of global change.
Great. Yeah. Also, I'm NBZ faculty.
I should have mentioned that.
So yeah, actually, if you're here to expect a finished talk and a lot of good conclusions, you're probably in the wrong place, because this is really going to be kind of a progress report. I want to throw out some ideas that we've been working with. Happy to get feedback, but it grows out of this effort that you've all heard about, the Berkeley Initiative in Global Change Biology. And the way I like to sum this up is actually something that John Hart said, and I can't remember where I first heard him say it, but I've heard him say it a couple of times. And what encapsulates this from my point of view is, as John says, if we knew everything about how the globe was going to change, if we had perfect knowledge of climate change, if we had perfect knowledge of how human population was going to grow, what still wouldn't we know about how biological systems are going to interact? So the focus here is really on the mechanistic change. What do we need to know about biology to make more reasonable forecasts as to what's going to happen on Earth under the pressure of all these global changes? And for those of you who are here for Liz's talk, you know how the museums fit into this. A very critical role. They played a role from the outset. What I want to talk to you about today is really kind of a progress report of the first major workshop that was run by the Big CB. This happened about almost exactly a year ago, not quite now. And the idea was to think about the theoretical framework. How do we think about global change, and what do we need to be doing differently in order to move the science forward? And that's where this idea about a conceptual framework for forecasting biological impacts on global change comes in. Basically, many of you attended day one of that workshop last year. The people listed on the board here spent an extra couple of days locked in a room, hammering out a bunch of ideas, and we didn't let them out until we thought something good came out of it. And then over the subsequent year, we have continued working together to try to come up with something that makes sense. And the reason I say it's a work in progress is right now where this all stands is we have a manuscript with Nature that we're now revising. It's come back from the first round of reviews. And we'll see what happens from there. Anyway, if you look at this list, you see that it represents quite a broad range of specialties. We're trying to think of this from the perspective of a lot of different disciplines: paleontology, network theory, maximum entropy theory, metabolic energy of ecology, and did I say network theory? Yeah, okay. And basically, start thinking about how we're doing forecasting now. There's a lot of biological forecasts out there, and actually a lot of good work being done in biological forecasting. Most of it sort of revolves around these basic concepts. Okay, we take a trajectory that we observe over the past or have reason to believe is happening and just project that into the future, and I'll give you an example of that. We think about projecting patterns based on modern baselines, that is, what we observe on the modern landscape today and various correlations and interactions, assume those are driving the process and project that into the future by forcing things in different ways, and things like species distribution modeling. The basic thing that all of these have in common, though, is we're taking modern day observations and just saying change a forcing factor by X amount and we expect Y amount of biological response. Okay, well, example of that. So this is out of a very recent paper in Science, projecting the amount of change we might expect to see in forested landscapes on Earth over the next 40 years to 2050. And depending on the model you use, if we have more sustainable meat production, for example, or if we limit climate change, or if we develop various global policies, you get different trajectories of change in how forest cover will either increase or decrease. But notice that for the most part, it's a pretty regular relationship. If you change the foresting by X amount, you get Y amount of change, and we just project that linearly into the future. We actually know that's not adequate. We know that's not adequate from looking at very simple examples like this, which this happens to be species distribution modeling, which a lot of us are familiar with. This is from Jenny McGuire, who this is out of her dissertation, which Jenny's now recent. But here are species distribution models for Microtus californicus, longicatus, montanus, oregoni, and townsendii. And if you look at the records today correlated with climate, you get that distribution. And then you can run that backwards, take paleoclimate models, say, okay, assuming we've got this right, let's project where we would expect to find these species several thousand years ago. And what we see is the species shows up in places that we miss by our modeling techniques. So, that's one example of how we're missing things. Another big problem is we're not accounting for interactions. We're not accounting for species interactions or feedbacks in a lot of our forecasting. And this is another example that I really like from the past because it's just very clear. If you think about mammoths through time and their extinction, and we just run a species distribution model and crank it through time, we find that during interglacial times, the last interglacial, there was a wide range, all the green through red, where that was decent mammoth habitat. The best mammoth habitat is the red, so that was much reduced. But mammoths made it fine through the last interglacial. Then, as we start getting into the coldest part of the last glacial, we find mammoth habitat is really expanded in terms of the prime habitat, the red, but also we see this line here, which is Homo sapiens coming up. Pretty much the same story 30,000 years ago. By 21,000 years ago, climate was warming. Mammoth habitat was, prime habitat anyway, was beginning to reduce. More expansion of modern humans. By the time climate changes so that we're back to this situation, the human migration wave has moved all the way up here, and mammoths are extinct, even though they have the same amount of usable habitat as they did during the last interglacial. So there's an interaction there that was important, right? That just a pure species distribution model isn't going to take account of. Now, that's great, but sometimes it doesn't work like we think. So if we expect that human population pressures plus climate change is going to cause extinctions, we also see things like this. This is out of a very recent paper in Nature by Lorenzen and Eski Villerslev and a lot of other people, and where they did pretty much the same thing I just showed you with mammoths, but in a much more quantitative way and with several species. Reindeer being one of these species. So if we trace reindeer ranges, and this is very appropriate, seeing as how we're getting near the holiday season, right? 42,000 years ago, 30,000, 21,000, 6,000. This is the projected range of reindeer based on species distribution modeling. We see that by 6,000 years ago, much reduced, proportionally just like mammoth range was much reduced. if we look at this panel down here, this is showing you the percentage of space that was occupied by both reindeer and humans, so the overlap, geographic overlap, through time, so 44,000 years ago, totally separate ranges. As you start moving more and more towards 12,000 years ago, lots of overlap in range, so a lot of human interaction. So you would expect, wow, reindeer should have gone extinct. Their populations crashed. That's what this line is. But genetic diversity didn't really do much. And they're still around in healthy populations today, okay? So here's an expected interaction that for some reason didn't lead to the loss of that species. So interactions don't always work like we think. The other thing, very important, that most of the trajectory-based forecasting doesn't take into account is the idea of tipping points or critical transitions. And there's a whole body of theory on this out there now. And you know, for example, Sheffer is a key person in this, as were several people in our workshop. But the idea behind tipping points or critical transitions is that we tend to think, as I pointed out earlier, you apply a certain amount of forcing, the system changes more or less linearly, so you can predict where you're going to be. That's great, unless there are these threshold effects, in which case you apply the same amount of forcing all along here till you get to this point, then all of a sudden you move very rapidly to a new state. Or even worse, from a forecasting point of view, you can get a situation like this, where small forcing, small forcing, small forcing, small forcing, then you get to this point, and the whole system flips and gets reset. And you can either force it in that direction or that direction, and you end up in a very different place in terms of ecosystem composition, operation, and so on. So this idea of critical transitions and tipping points is actually very key to be thinking about. We know that happens. We know that happens on many different scales. And a wonderful example came out since our workshop in this Estesinol paper, and ties very closely into the network theory and food web theory work that we were doing in the workshop. Basically, by pulling, in this case, sharks or higher large reef fish out of the system, you go from something that looks like this to something that looks like this very rapidly. And likewise, in terrestrial environments, you see the same sort of thing. Pull wildebeest out of this system, you go from something like this to something like this, okay? And if you think about what's really driving that change that you see on the screen there, it's changes in energy flow. It's changes in how energy flows through the entire ecosystem. And that's where the metabolic theory of business comes in what we were talking about in our workshop. So energy flow is key. We haven't been thinking about how energy flows through systems. And then finally, well, maybe not finally, but another very key point is that we talk about tipping points, and we talk about food webs collapsing and so on, but really all of these are examples of complex systems, and all biological systems are complex systems, okay? Complex systems are basically defined by having, different nodes and different connections between nodes. So you think of a gene, you think of metapopulations. Any biological system you think of reduces or scales to a complex system. So it doesn't matter what you're studying, you're really studying complex systems. So then you have to start thinking, if you're thinking about changes, you have to start thinking about changes and the way complex systems change, which involve critical transitions and tipping points, because you can pull out some connections and it doesn't matter. You pull out other connections or nodes and the whole thing falls apart. So some are more important than others. Okay, so we've got all those things we haven't been thinking about, and then you start thinking, well, how am I going to define if my complex system is about ready to hit a tipping point or something? Whole business of scaling becomes very important, both temporal and geographic. So in this little chart, you're going through time here, and you're seeing lots of wiggles in the system. And depending on your scale of reference, you could say, oh, this is one state from here to here, characterized by that much fluctuation. Or you could say, wow, look at all these critical transitions, this to this to this to this. So it becomes very important to, as you're designing a study or thinking about it, to specify the scale, temporal and geographic, at which you're working. And then the trick is to start thinking about how does what I do at my scale connect up with this bigger scale or with this smaller scale, and what are the interaction effects. Okay, so that's kind of where we were at the end of the workshop. And where we have come since then is thinking, wow, everything we're seeing is actually saying that critical transitions happen not only at these small scales, but at the global scale. And as I'll show you, I think there's probably really good evidence that we're approaching one of these global scale critical transitions. Now, before you say, yeah, right, you know, these things happen. They've happened many times in the geologic past. So, you know, we're going through geologic time here. And basically, you don't have to read all this fine lettering, but every one of those things indicated on there is a critical transition in the Earth system, and they happen at different scales. The ones you're probably most familiar with are these arrows at 400 and some million years ago on up to 65 million years ago. Those are mass extinction events, okay, where Earth's system was basically reset. Those are the big scale ones, probably more pertinent to the sorts of critical transition we're thinking about now, is the interglacial cycling over the past 2.5 million years or so. And glacial interglacial cycling, where you're going, bouncing back and forth between a true icehouse world and an interglacial world like we live in today. And in fact, these the transition from the last glacial into our most current interglacial exhibits most of the mathematical properties of a critical transition. And I'll point out what those are in a little while. But the thing to note now is there are quantitative ways to characterize critical transitions, and these Earth system things are critical transitions in that sense. So they happen. Now, are we in one now? Okay. Are we approaching one? Well, one of the ways that you recognize critical transitions is if the rates of change in various important markers are much faster than normal, and we'll have a discussion about normal. And if you look at things in terms of rates of change, yeah, absolutely no doubt. You know, we hear a lot about climate change. Here's a paper from Jessica Boyce and Liz. And what's going on here is you're plotting rates of climate change through time and standardizing that by the interval of time over which climate change is measured. And the point being the normal rate of change is indicated by that line. These are the rates of change, the lowest and highest, that are estimated now. And actually, we are at these higher rates of change given current trajectories. So we are way outside the range of normal compared to the past millions of years in rates of climate change. That's important. Population growth. More or less normal population growth for the human species till you get here, and then there we go. Okay, we're at right here now and going up, probably to right here by 2050. That's probably important in terms of thinking about critical transitions and energy flow. And here's why we know it's important thinking about energy flow, all right? This is out of one of my papers on charting megafaunal biomass through time. So people are megafauna, we are megafauna, and if you calculate the total megafaunal biomass, that is the bodies on Earth that weigh more than 100 pounds, and track that through time, start back here at about 100,000 years ago, and then you go, things are more or less steady for quite a long time. We hit this point, which happens to be where human populations start their exponential rise, and there's a crash in biomass as a lot of other species go extinct. Then we build it back up, mostly with people and domestic animals now, and then it just keeps on going and going. Now, the point here is that this is probably the normal megafaunal biomass for Earth, based on sunshine coming down from Earth, converting energy, and so on. At this point, where our bodies and livestock really began to skyrocket, is actually the beginning of the Industrial Revolution. This is where we really start to dig coal out of the ground. We add energy into the global ecosystem. We appropriate most of that energy. We have substantially changed the energy flow in the global ecosystem, not only by appropriating, but by adding, okay? Habitat fragmentation. I don't know if you guys saw this paper by John Foley and colleagues a couple of weeks ago, got a lot of press. But the upshot of that story is that this is what about 40% of the Earth now looks like, okay? 40% of the Earth's land, and there's the 40% that's agricultural land in some form or fashion. We have dramatically changed the planet, and that has all happened in the past 100 or so years. That has effects, right? Rates of extinction that Gwen and several other people, Caitlin, Emily in this room, in addition to me, have worked on this paper. But the point being, here's the range of normal extinction rates through geologic time. Here's where we are in extinction rates over the past 10 years or so, probably outside the range of normal and standardized for interval length. Here's where we are should vulnerable, endangered, and critically endangered species go extinct, way outside the range of normal. So very, very clear that we've increased extinction rates, again, thinking back to how global ecological networks are constructed. This has big impacts. And there's the kind of impacts we're seeing. Okay, so we're now dead zones along the coastal areas are quite common. That's what they look like in aerial view. Those agricultural lands are, for the most part, replacing highly biodiverse areas with monocultures. Scott Lowry's and David Ackerley's papers have shown how the velocity of species range shifts are not only going fast, but probably not fast enough to keep up with climate change in terms of, especially when you take into account these sorts of landscape effects, changing the phenology of the species, and so on. We're seeing novel communities come into existence as primarily from invasive species. We're talking about assisted migration to help manage species extinctions and loss from climate change, dramatically changing the planet, okay? And then the whole point of that Eskimo paper that I showed you earlier is that there's actually been global trophic downgrading. We have essentially lost the top trophic levels for most natural ecosystems on Earth. Is that a global scale critical transition? Are we seeing that? Well, we don't know. And you know, I think this is where we need to start thinking about what we're doing in forecasting global change. So what we're doing now is we're monitoring at small scales, just for, you know, that's what we have to do. A person can only do so much. Your study plot can only be so big. You can only study so many species. So most of our data is from small scales. We see these big overall patterns, but if we're trying to conserve a particular landscape, for example, is that still possible? And can we use information from those smaller scale landscapes to really say where we are in this global state shift trajectory? Because, you know, that's what we have to do. Everything we're doing is trajectory based. Is that going to be sufficient to, well, another way of saying that is a global scale state shift the sum of a bunch of little local scale state shifts, or is it something bigger that is driven from the top down? And the critical thing, I think, for this big CB effort is, how do we figure that out? You know, that's the $64,000 question. So that's where this whole business of thinking about a new conceptual framework for what we're doing, how can we take our individual studies and plug them into something bigger? And I think this is really the punchline of what I want to tell you guys today. So this is something that our group has come up with to think about, and you know, maybe it's right, maybe it's wrong, who knows? But the idea is that we're trying to get, ultimately what we're interested in is this global ecosystem picture. Are we going into one of these shifts that something weird's going to happen to Earth that we just can't predict, or can we actually see where we're going? So if you want to get to that level, first of all, we said you have to start thinking of the whole global ecosystem as a complex system, but it's not one big complex system, right? It's a big complex system that's built of a bunch of much smaller nested, ever nested smaller complex systems. So, you know, global ecosystem, we've got a bunch of different biomes, for example. And you can think of each biome as a complex system composed of many interacting species. So in this little diagram, we've got Earth, several different biomes. Each of those biomes has a bunch of species represented by the different colored dots. Those species interact in ways connected by these lines, okay? And what we're really trying to do when we're monitoring the global ecosystem is we've got a whole bunch of studies at small scale systems, and we're trying to define some sort of range of normal and say, are we going outside that range of normal? We're also only doing that at one point in time. So the whole key here is to think about, all right, what would we expect to see if we continue forcing climate, population growth, whatever forcing you want to put on here, how would we expect to see the trajectory of the system change through time, right? And what would we look for? And what is the right range of normal? So I'd say the right range of normal to be thinking about in terms of a global state shift is, how does the change you're seeing in your system compare to the range of variation over the past several thousand years, back to maybe 11,000 years, because that's where we kick into the interglacial state. So I would define the range of normal as typical for this interglacial. Now, how do you do that? Well, there's, you know, we all have our study systems. You can look at gene frequencies and come up with ways to assess how they may have changed through time and whether that amount of change is more than you would expect. Metapopulations, you know, density patterns, whatever. There's a lot of different ways you can do it. Food webs. But I think the key is to not just think about, oh, I saw this amount of change in X number of years. The key is, how does that amount of change compare to a longer time period that's relevant to defining normal? And that gets tricky. Now, the second part of it is, what do you expect, if you're talking about a global scale state shift, what do you expect to see through time? So we're going through time here, and we have our forcing functions, and as the global ecosystem begins to change into something else, you know, there's a lot of different things you can look at. So, for example, if connections between biomes in this case, here, more strongly connected than here, for example. Looking throughout an entire biome or a region like California, are you seeing significant amounts of change at every study, at all study systems in many different places, or are you just seeing certain kinds of systems change? So is there signs of some sort of cumulative effect? And then you might expect that as local effects accumulate, or as global forcing gets stronger, these kinds of connections between systems, and here I'm saying biomes, but you know, you could talk about metapopulations, you could talk about any kinds of connections. You know, at some point, you begin to see enough change and certain kinds of changes that you say, wow, this is getting outside the range of a normal fluctuation in my system and exhibiting signs of a critical transition. My system is starting to flip. And what do you look for that? Well, as I said, there are certain quantitative signs that are very important, and most of these require some level of time series data. So you do have to track things through time or find ways to do that. But these are sort of the key indicators, all right? So slow down in recovery to perturbations. If the system is disturbed, how long does it take to come back to normal? Increasing variance. Are you beginning to see a lot of boom and bust cycles, for example, where you didn't used to see those boom and bust cycles? Increasing autocorrelation between fluctuations. So if you have a large fluctuation this next 2 years, do you get a similarly large or even larger one the 2 years after that? Flickering, more rapid shift from one condition to another. And then indicators that how energy is flowing through your system is changing. So, you know, these are things I'm not going to dwell on, but especially if you read the Sheffer literature, that 2009 paper, it's all nicely spelled out. But the idea is by thinking about local systems in these terms and beginning to put that data together, it may then actually become possible to say, where are we in this trajectory of change? And the big question, in my mind actually, is, are we at this point or this point? This point being sort of past the tipping point. There's nothing we can do to stop it. And we just keep going into the new state. This point being, we still have a chance to sort of guide the future in some direction we think is important. And I guess I would say my intuition, and actually hopefully a little more than intuition, based on the data we've been looking at over the past year, is that we're probably at this point. And the reason I say this is because our network guys and John and his Maxent group have actually demonstrated that there's certain long-term stable properties of the networks they've been studying, and John in interpreting macroecological patterns with Maxent, that in fact are still exhibiting the patterns that one can document for farther back in time. So I think that means we haven't shot past this point yet. But all of those macro scale forcings that I was showing you early on, you know, climate change, human population growth, and so on, in fact, say that we're pushing pretty hard, and we might expect to see some changes by those metrics that we can see in Maxent and network patterns and so on. So I don't know. I think that's probably that's the upshot of this paper we're trying to get out now, is that we're probably at this stage, and that there is, in fact, some guiding of the biosphere that we can do. Don't know. But clearly, what we don't know, and what we need a lot of information on, and what people in this room can actually contribute to in a very major way, are these sorts of questions, right? I mean, in your system, is it valid to project as trends? Are you seeing warning signs that maybe the trend-based projection isn't going to work? That relies on really understanding whether the changes you're seeing are anything unusual. Every biological system changes all the time. So just because you see a change doesn't mean it means anything, okay? So looking for change isn't enough. It has to be set in some context. And then here's a question. If you're thinking about global scale state shifts, do they happen because a lot of different places, a lot of different systems on Earth are affected by different causes, and it all sums, and then there's a sort of multiplier effect as you go up scale? Or does it happen because there's this big global pressure that is just driving change everywhere? Is it a top-down or bottom-up sort of issue? And you know, I don't think we know that. I mean, yeah, we know that people are driving a lot of this, but we don't know if a change in a prairie system in Texas has anything to do with a change in the Serengeti in specific ways, right? So does seeing a change in one mean that eventually you could predict a change in another? So anyway, I think these are the kinds of questions that are sort of the next step in studying this whole issue. Okay, well that's really my progress report. We still have some time left for discussion, and I'm happy to discuss.
I've got a couple of questions. I'm not quite sure how to frame either one of them, but I'll try. So, change happens, as you said, but the perception of change is that it's either good or bad, rather than indifferent.
Right, right.
And those perceptions differ depending upon the person you're talking to, okay? So there's a whole community out there in the world that could care less about this.
Yeah.
So or if they did care about it, they'd say, fine, this is exactly the kind of change that we want to see. So at what time, you know, in your group, did you guys talk at all about at what stage do you shift from an academic exercise to actually trying to do something beyond that? And at what stage, I don't know all the people on the list, I recognize a lot of those names, but you know, are there political scientists and social scientists engaged in this effort? And so what is your ultimate goal of trying to,
well,
other than just describe, you know, are we reaching a tipping point?
So I would say the ultimate goal is to understand whether we really have anything to worry about in terms of biological collapse. Is the biosphere going to really change in such a way that our way of life as humans is going to be severely less quality than it is now? That's what most people are interested in, right? As long as our quality of life, you know, as long as we have these nice buildings, these great universities, our nice houses, our DVDs, most people don't care, right? So you know, food to eat. But the problem with a global scale tipping point is that's exactly what's affected. And once those global survival resources are impacted, all hell breaks loose socially. So I think that's the ultimate question is, as biologists, can we predict whether or not something like that is a reasonable assumption? And if it's a reasonable assumption, or not a reasonable assumption, if it's a reasonable conclusion that there's even, I would say, a 10% chance of that happening, we don't want to go there, right? Because once that happens, humanity as a whole takes a nosedive. So that's the first part of your question. I probably didn't answer. The second part is, are there social scientists, political scientists, and so on involved? Not in our group, but absolutely lots of other groups are working on that and interacting with the biologists. You know, a huge group at Stanford doing that, for example, several other universities. So that interaction, yes, is the ultimate goal. And the big CB, as it currently stands, is primarily, as I said at the beginning, if we knew everything about everything else, what wouldn't we know about the biology? Because that seems to be actually the missing piece of the puzzle. Emily and Dave.
I'm a little concerned or curious about your method of using the last trends or patterns over the last 11,000 years as a baseline, because I think, you and Mark and other colleagues have pretty well demonstrated that the last 11,000 years is not necessarily correlated with the previous 50 million years, at least in terms of biodiversity and body mass energy in mammals. So I'm wondering about, is that really realistic?
So I think that the reality of the situation is, for the last 11,000 years, people have been fairly abundant on Earth. So that's different than anything that came before it. And the goal isn't to get rid of people and return to some pre-people state. So I think we have to, at least that's not my goal. So I think we have to be realistic and say, all right, what we're talking about is humans as a major part of the global ecosystem. We've been ticking along pretty well for 11,000 years. What's the chances that we're going to be able to keep going and doing that without causing major damage to ourselves as a species? Dave.
Well, there's so much momentum in the system now that I mean, we see how difficult it is just with the current human population and the growth trajectory that is there. And in everything, I think there's already so much momentum in the system. We're heading someplace.
Yeah,
we don't, as you say, we don't know.
Yeah. We
don't know if we've got the tipping point, but we're moving. We're not staying still. Right? We're moving.
At a very fast rate.
Yeah.
Yeah. Yeah. So is it even possible to put on the brakes? I mean, so that goes to, you know, are we at that stage 2 or stage 3?
Right.
I don't know. I don't know. And I guess the reason I think it may still be possible is because you can take the half empty, half full philosophy, right? So half of Earth's surface is already human dominated, but half of it is not. Can we save that other half? Can we do anything that's going to keep that other half functioning in a way we want it to function? And the short answer is I don't know. And if we did know, we wouldn't have to do this kind of stuff. Jim.
Do you have to me this feels like it's really already a political argument. I mean, you already know that this is happening and that we have to stop it. And so have you guys developed any sort of game plan or strategy, or have the political people identified a sort of game plan that might have some hope of convincing the general population that something needs to be done about this? I mean, is there or could you have like road markers, like when we get to here, if you have a forecast, maybe if you're only partway down the line, you can stop it. But in general, it seems like human beings just won't respond to anything until there's a catastrophe.
Well, yeah. So I mean, the short answer is yeah. There's a lot of people in the political system who want these answers from scientists. I mean, if you go to Washington and knock on the door of the head of Fish and Wildlife, and I know this because Liz did this when we have these discussions. They want to know what's the scientific basis for whether or not we're going to lose pikas, and is that going to matter in the broader picture? And if you tell me it does, we can set some benchmarks and try to make it happen. But if you tell me it doesn't, I'm not going to bother with that.
I mean, in the global, when you think about the global perspective, but that's kind of small potatoes, right? I mean, you really need to convince the politicians,
right.
And the only way to convince the politicians is for the general population to have a groundswell of concern about this, and we're going in the opposite direction, it seems like.
Yeah, no, I agree. So that's where what we do as scientists isn't quite enough. I mean, it has to be based on science, but if it just stops with the science, we may as well not do it, other than for fun.
There has to be a strategy.
Yeah, well, there absolutely has to be a strategy, and there are those strategies out there building, growing. I don't know if you're familiar with the MAHB group, MAHB. I can't remember what that stands for. Millennium Assessment of Humanity in the Biosphere. It's like a global network of people that are working towards this. So it's hard.
Do you think that it can be led from the United States, or does it have to happen outside of the United States?
The US is not signatory to any of the
I know. I mean, that's the thing, right? It seems like this has traction everywhere else, just not here.
They're busy meeting in South Africa at the moment to discuss climate change, and the big first world countries are saying, we're pulling out, we're not signing anything, we're not agreeing to any deals, and the little countries that are, going to be flooded are saying, please, please, please help us, and the big countries are just saying, we don't care. So that's what's happening at the moment.
Yeah.
So, yeah, Iraq.
Yeah, and I mean, actually,
It's
everywhere.
US and China and Russia.
Everywhere I give a talk on this stuff, if it's in a different country, that's actually the first question. Well, the U.S. hasn't signed on to this, and I used to say that. Well, now that we've got Obama, that could change. But, no, I can't say that.
My general impression is that people have accepted that we're in a very dangerous state. Mm-hmm. I think even those people who are denying climate change and all that, I think they've just sort of at some level accepted that it's going to get worse. And they're just, and I mean, that's kind of shocking to me. But I think I see a lot of evidence of that. Mm-hmm. That people have just accepted that things are, it's just going to get worse. And so, and they live with it, and that has to do with the third world countries and countries that are going to be flooded out. Well, the attitude is, yes, that's going to happen.
So,
yes, we're going to lose a lot of people in Bangladesh, you know.
And Florida.
So you know, I agree with that, but I would actually say that we as scientists are to some extent at fault.
Yes,
Because
agreed.
we have done our science, we've said, wow, this is really cool, you know, I discovered this or that species, and it stops. And oh crap, that one's going to go extinct. But we're the ones, you know, we're the major university. We can be teaching this stuff. We can be reaching out. We can be blogging. We can be writing op-eds. We're not doing it.
We may also be flattering ourselves here.
Well,
I think that doing that will really change the wheels. You can throw yourself on the wheels.
well,
and
yeah, but you
can
know.
have some influence, but it's going to take more than the academic community.
Oh,
doing those
absolutely,
things.
absolutely, absolutely,
And
yeah.
I don't see it, and also, I'm not sure everybody would agree that we're in a dangerous time. I think people would say we're in a changing time. And so some of the answers to your
that's right.
questions there as to how dangerous those times are going to be are, you know, I think are important.
Yeah, yeah.
But they'll also be very, I think they're very hard questions to answer. I'd like you to see, I mean, you mentioned characteristics, but maybe testable hypotheses
Mhm.
could go along with it so that it doesn't just become only, you know, based on opinion,
Right.
but
Yeah, yeah.
allow some way for you to put these things
Yeah.
out in a way that people can then start amassing those facts.
Yeah, that's the key thing.
It's a challenge to do.
It's a huge challenge, but that's exactly what's needed, you know. I mean, I think there's sort of two steps to it. One is for people to start thinking about how what they do connects into a bigger picture. And the other is to, as you say, come up with concrete ways to build the data and ask the right questions that give the right answers. So yes, I agree.
And one of the pieces that I was kind of looking for in answering this question of, you know, is where don't we have perfect knowledge that would actually affect how we think about
Yeah.
these effects?
Yeah.
A lot of your analysis was really at the system level.
Mhm.
And it seems like in a way we're still a world away from understanding, you know, the individual, the species level questions to help us
True.
figure out
Yeah,
how some of those
yeah,
systems work,
yeah.
where local adaptation is going to take place, if
Mhm.
it already has, what to expect from, you know, variation among individuals, among species in responses to these things.
Yeah, yeah.
As well as the interactions. It seems like we're, you know, scaling those things up to the system level is still a real challenge for us to do.
Yeah, and you know, I think probably a take-home message is that we're approaching these problems from a multiplicity of directions and multiplicity of study systems and scales. And I think there's not enough interaction between people working at, you know, the species level versus the ecosystem level, or the, you know, the genetic change level versus the ecological interaction level. So I guess that's really a very key point that you brought up that is really important. Is if people are thinking about a common huge problem, then there's a way to connect up those different scales and start talking to one another and say, oh yeah, well, you know, this would be a good way to approach that, or my understanding at the species level kind of tells you something about why you're getting that interaction. So yeah, agree 100%.
Further questions for Tony? Okay, on that happy note, we'll